Welcome back to the Foundations of the Computational Economics course. In video 33 we will talk about random numbers in Python and Monte Carlo methods. So when we are talking about random numbers and simulations, which is immediately connected topic, we may have in mind three different things. So the first situation has to do with the theory of probabilities, the analysis of the situations when we know the distribution laws of this randomness that we're working with. Now, in mathematical statistics, the problem is a little bit more complicated. We usually know a family of distributions where particular data may come from. And by data, I mean a collection of usually independently obtained draws from a particular distribution. And now, econometrics is an application of statistics in economics. In this video, in much of the course, until the very end, we will primarily have in mind the first situation, the theory of probabilities type of setting, where we know the distributional laws of the underlying randomness. Just to make sure that we're all on the same page, let's remind ourselves a little bit about the theory of probabilities. So a random variable x tilde, and in this video I'm going to use tilde to denote random variables. A random variable x is a combination of three mathematical objects. The first one, omega, gives the set of all possible outcomes for the random variable. This Gothic A is the sigma algebra of the events. And this is basically a rigorous way to describe all possible subsets of the set of omega, of the set of all of the outcomes. And of course, by an event, we mean a particular subset of all possible outcomes that may or may not happen. And finally, the third component is the probability measure, which is a normalized measure over the elements of the sigma algebra A. And so this function essentially gives the probability of various events, which we can rigorously define for the random variable x tilde. Now, depending on the nature of the random variable and corresponding definitions for the three components of this complex mathematical objects, we may talk about discrete random variables, for example. And in this case, the omegas, the set of all possible outcomes, is a finite set with particular values, say n of them. And then the all possible events are described by all subsets of omega, and there is a finite number of these as well. And the probability measure for this random variable can be constructed from the probabilities of each particular outcome. So p1 corresponds to x1 and pn corresponds to xn, and so forth. And then we just have the formula which says that the probability of an event for any event in the sigma algebra Gothic A is the sum of the elementary probabilities, it says here. Now, the cumulative distribution function I've written here is a definition. For the discrete variables, that's not used all that much, but we can write it still, and it will be a stepwise constant and discontinuous function. Now, if we think about a continuous random variable, then the set of all possible outcomes is a set of real numbers. And here I'm thinking about a scalar, so that r is just an r, not rn, for example, which could also be defined. The sigma algebra is a Borel set of omega, and again, this is a rigorous way to define all possible intervals and collections of intervals, so unions of intervals of the set of real numbers. And now the probability measure is given with the help of becomes a really useful, namely the cumulative distribution function of this continuous random variable. And so the probability of the random variable falling into the interval AB is just the difference between the CDF calculated at B and CDF calculated at A. Now, the CDF cumulative distribution function is then exactly equal to the probability of the random variable to fall below a particular value x. and it can be expressed with an integral where the small f of t is the probability density function also associated with this random variable. Now, as we all know and remember, the first moment of a random variable defines the central tendency, and that's what we call an expectation of a random variable. And it's in general case, it can be written as this, what's called a Lebesgue integral over the distribution f of x. And then in the two cases that we've considered, it's either an integral, a real integral, where we also have to insert the PDF, the probability density function, or it's just the sum of the possible values and associated probabilities. So this is how we calculate the mathematical expectation of a random variable. The second central moment of a random variable is the expected, the expectation of the squared distances between the realizations and the expected value itself, and that's what we know as the variance. The measure of variability of a random variable. And then, of course, standard deviation is the square root of the variance, and it's measured in the same units as the mean. By random sample, we understand a series of independent draws from a particular random variable. And as I said, we will focus here on the case where we do know the underlying distribution of this random variable. And so these are independent draws from a normal distribution. And you know, we write it this way. So they are all distributed according to this distribution of the x tilde. Now, when we now talk about simulations, this is essentially the same as drawing a random sample. So simulating something is basically drawing a random sample from a known distribution. And what's important to understand here is that economic models that we've been talking about and that we've been coding up, economic models can be also thought as it's just complicated distributions. The economics models, which includes randomness, so shocks, in other words, with some assumed distributions, they, as functions of these variables, also become random variables themselves. And there's what we can call an induced distribution that is induced by the econometric model or the economic model itself. And so simulating the economic model, or sometimes we say simulating from an economic model, means that we want to draw realizations of this complex distribution that is induced by the economic model itself. And then, of course, as we change parameters of these models, then the underlying distribution or the induced distribution also changes. Okay, so with this background sort of out of the way, and having the same understanding what the simulation means, let's talk about the technicalities. And everything starts with how do we generate random numbers in a computer? Well, it turns out that pretty much every language, every programming language, has a function that somehow returns a uniform number between 0 and 1. That's usually a rand function. Well, that's because simulations are really useful in many areas of computation in general. It's important to know that these functions are not generating something completely random. Instead, they are returning numbers from a pseudo-random number generator or a sequence of numbers which look sort of close enough to being random. And you know, when I'm not mentioning the distribution, that's sort of like a convention. When the distribution is not mentioned, that means that the distribution is uniform. So random here means uniform on 0 and 1. So what do we want this function? What properties do we want this function to satisfy? Well, it must be fast so that we can use it in loops and over again. And it has to satisfy certain statistical properties. So if we approach this generated numbers as something that comes out of a distribution not known to us and study this underlying distribution, then we should not reject the hypothesis that the underlying distribution is indeed uniform on 0 and 1. Moreover, these realizations have to be independent, or have to not reject the independence tests, and they also have to be stationary. So as we generate more and more data at any point of time, these numbers should be looking in the same, essentially, from the statistical point of view. And now, because this is a pseudo-random number generator, you could think that, and you would be right to think that, these numbers repeat after so many are generated. And that's what's called periodicity. A good random number generator has to have a large periodicity, so that, it takes a lot of numbers before they start repeating themselves. So here's a picture of some random generated bits. Right, and every dot here is black or white, according to the generated 0, 1. And you can see that, sort of if you look at it from a distance, this is pretty random. I mean, it's kind of hard to say that these black and white dots are forming any particular patterns. Now, on the other hand, you may say that there are these vertical lines that you can see, and maybe there are some waves that go in this way that you could see as well in this picture. Or I don't know, some lines going this way. It's kind of hard to say, right? Well, but this is a graphical representation of one of those pseudo-random number generators, and that's actually a particularly bad example, where even though on a larger scale these numbers, these generated random bits look quite close to sort of white noise, right? A completely random thing. If you squint your eyes, you can see some patterns. Now, so the pseudo-random number generators have to be distinguished from these true random number generators that some of the companies like random.org produce for the researchers and practitioners. Or there are hardware random number generators, which may use thermal noise or electrical noise, something physical, to actually generate randomness in the true random way. Okay? And if you look at what these random numbers produce, well, this is really hard now to find any sort of patterns in this picture. But I guess for our purposes, we're not doing cryptography. We're just looking at the simulations from the econometric models. For our purposes, the quality of random numbers that we use in our models is not that critical. All right, so in Python, there are several modules that help you with random number generation. The simplest one is just random. That's the model by itself. It provides basic functionality in scalar numbers. There is a section in Numpy or submodule numpy.random, which produces vectors of random numbers and has many different distributions to generate numbers from. And then there is a more statistics-oriented SciPy stat. It has more statistics functions. But here's the easiest way to generate a random number between 0 and 1. And of course, you remember that we've done this many times actually already in this course, without talking more fundamentally about it. And this video is covering or is trying to put some fundamental knowledge on the table about this random elements in our models. So here's the simplest code, right? We import the random module, and then we call random.random, which, as you remember, generates a scalar uniformly distributed between 0 and 1. And we do it for 100 periods and print them. It's a range of 100, but I guess we're printing just a few of them. Yeah, I should say that this is a list comprehension, as you remember. So we are generating a random number of 100 times, and then put everything into the list X. And if I instead of this, if I just print X, then we'll see a lot of it's 100 numbers between 0 and 1. And here I'm only printing the first 10. By the way, what does this star mean? If I remove the star, what we have is the list of 10 numbers, right? And the list of 10 numbers, that's because of the slicing here. And then I want the separator between the two printed things to be a new line. This is the notation for new line. But then, of course, new line doesn't happen because this is just one thing that the print is printing. Now the star is converting the list that I give it here into the list of arguments. And so now instead of this being just one argument, we're actually giving to the print statement 10 different arguments. And then they can be separated by a new line. Okay, let's look at the Numpy generator. And here is a little function that I've written to visualize the random data generated by different calls. So it can build a histogram of the data. We can change the bins that the histogram is using, or the range. And then there is a possibility to draw a theoretical line sort of on top of the histogram. And that's what's happening here. It just draws on some lin space for the given range, and if the range is none. If the range is none, then it uses this 100 points, and it just plots the theoretical line that I can also give it, and then it can also plot CDFs in principle. Okay, so now let's import SkyPy stats, and from there let's use a uniform PDF distribution as a theoretical one, and access still come from this random generator. What do we have? There we are. So these are the generated x's drawn as a histogram between 0 and 1. They are all between 0 and 1, and the height here corresponds to the fraction of the generated axis within particular bounds, right? This is what defines the bins. And here's our theoretical distribution. You can see that it's not very close to the theoretical PDF, but does it have to be with the number of axes that were generated? We don't know. Let's run a loop. So in here, n is going to be 10 to the power of I. So from 1, no, we're starting with 1. So from 10 all the way to 10 to the power of 5. We will generate now using Numpy. This is random, which is also uniform between 0 and 1. And then we will show it using 25 bins. And again, the theoretical distribution is going to be the uniform PDF, which is just a flat line. Let's title it, add a title. How many realizations? So with 10 realizations, the data looks pretty far from the PDF, theoretical PDF, but you can see as we're generating more and more data, then it looks more and more like a theoretical PDF on the histogram. And this is, of course, expected. This is this is implied by the law of large numbers, essentially, that we have this conversion. And you can see that the generator that we're using here, the Numpy random, does generate data which conforms with the theoretical property derived in statistics, essentially. Okay, so what are other distributions that we can generate data from? Often used in econometrics, well, economics more generally. Normal, log normal, exponential, F distribution, or chi-square distribution. There is a whole list of distributions that Numpy supports, and they're listed here. And we can draw similar pictures to what we just did with uniform distribution, where we are drawing from log normal. Log normal is useful because it's a distribution on the positive for the positive values, and you can have expectation at 1, right, for the standard normal. So log normal is just the log of the normal distribution. And this is a very useful distribution to describe returns in economic models. And as you can see here as well, as we generate more and more data, then the histogram starts to look a lot like the PDF. So what if you need data generated from the distribution which is not on the list of the supported distributions in the package that you're using? There are several things that you can do listed here, accept reject method being quite popular within Bayesian statistics, for example. Sequorad algorithm is based on the graphical properties and has to do with integration as well, actually. You can read about it here. So in this class, we will focus on the inverse transform sampling, which is a wonderful technique, actually. So imagine that you have to generate from f of x, and this is a CDF of the random variable of interest, x tilde. We will assume that the f to the -1 of x, the inverse f of x, is well defined. Well, then the algorithm is elementary. Let's simulate the numbers from the standard uniform distribution, so uniform distribution on 0 and 1, and then return the inverses f of x calculated at the generated numbers. And these are going to be the realizations from this distribution f of x, which is the distribution of interest. Extremely simple. So why does it work? Let's assume that the x tilde is the random variable x is just the function of the random variable u tilde, which has the uniform distribution on 0 and 1. And let's denote the CDF of this x tilde variable with the corresponding subscript. Now the fu of x is given by this formula here, which is essentially, if you think of the shape of the CDF, this is going to be looking something like between 0 and 1, this is a 45-degree line, and then it's exactly 1 and exactly 0 before and after. Okay. So how does the argument go? Well, let's write the definition for the cumulative distribution function of this variable of interest. That's the probability that the x tilde is less or equal a particular value that comes here. But we know that x tilde is just the inverse CDF of f, right? And then we can take the f of x, the function applied to both sides of this inequality. We know that CDFs are non-decreasing functions. So this application of monotone, weakly monotone function, at least weakly, does not change the sign. So the sign holds here. But now what's written here is the probability of the of a particular random variable to be less than or equal to a value, and that's the definition of the CDF itself. So we can have the CDF of this random variable u applied to this value here. But then, of course, this value, the values returned by f of x are all between 0 and 1 by definition of a cumulative distribution function again. And so applying this, just because it's in the appropriate range, simply returns f of x. And so what we have is that the CDF of the interest of the variable of interest is given by f of x itself. And so this simple proof shows that this algorithm works. It's enough to just generate uniform random variable, the simplest random variables, and then apply the inverse CDF transform to get the realizations from the random variable of interest. All right, this is the picture of the same thing. You can see that the CDF shown here in green is a transformation from all possible values into the interval 0, 1 of quantiles, and then the inverse is the transformation of the interval 0, 1, where you can generate standard uniform into all possible values, and that's exactly how it works. So here's an example. If you want to generate realizations from extreme value type 1 distribution, it has a CDF like this. Writing the inverse is not that hard at all, and then you can apply the described technique to generate from Gumbel or extreme value type 1 quite easily. Okay, sometimes in economic applications, it is useful to have repeated simulations. So the simulations that the random numbers that you want to make sure are the same in different runs of your program. And for this, there are several tools provided by Python. And first of all, this is what's called the seed of the random number generator. We can fix the seed. We've done that before. In previous videos, we can fix the seeds to a particular number, and then once it is fixed to a particular number, then the random numbers that follow, they are guaranteed to be the same every time we fix the seed. The same thing with get state and set state of the random number generator. We'll see how it's used in practice later as well. Okay, now let's talk a little bit about Monte Carlo method. In general, Monte Carlo is the approach where to solve a deterministic problem you use random numbers. So here's a classical example. Let's compute pi. And in this setup, consider a circle with the radius 1. Okay, so what's the area of this circle? This is pi r square, but r is 1, so it's pi, right? So the area of this circle is simply pi. But we will focus on this square here, which is a unit square. And so pi will be the area of the red dots multiplied by 4. Okay, the approach is that we can throw dots randomly into this unit square, and then just take the ratio of the number of dots that fall within the circle to all the dots that we have thrown into this square. And this will be approaching, as we throw more and more dots, to the ratio between the area of the circle and the area of the unit square. Okay, how do we implement this in the code? Let's write this very simple function. N is going to be the number of dots used for the calculation. We will use Numpy, random uniform for uniform distribution. By default, this is going to be a distribution between 0 and 1. And the size of the array that I want to build here is going to be 2 by n. 2, of course, for 2 coordinates of the dots. Now, let's see how can we check that the dot is within the circle or outside. Let's just calculate its distance to the origin and compare that to 1. How do we calculate the distance? We take the square of the coordinates, we sum them along the 0th axis, which is the first axis, or the vertical axis, right? And then that's going to be it. That's the square root, the square of the sum of squares of the coordinates. And then we have to compare the square root of that to 1, or the just that value to 1 square. And that's what we're doing here. We can skip the square. So we just compare whether this quantity d2 is less than 1. And this is either true or false. The sum of this will give us the number of points which are within this circle. And then the ratio is just going to be the quarter of pi. The pi is going to be 4 times this S4. Okay, if we run this, we will get a value with the 10 to the 6th of points. We'll get a value of 3.1399, which is not particularly good. Well, at least, in several runs, we'll get something which is closer to 3.14. The bias is given here, so the bias in the third digit. As you can see, we are here we get a bias in the minus of 5. Because this is a randomness-based approach. Then, as we run it many times, and I'm just rerunning it by pressing the Shift Enter here, we can get we get different values of approximated pi. So let's try to do it in a loop and collect. We don't need data here. Let's just do it in a loop, and I want I to denote the power of the. I want I to denote the order of magnitude in the number of points. Okay, let me run this. And so here, what's the interest? My interest is to see how the error declines as we add more and more points to the Monte Carlo calculation of pi. And as you can see here, the bias, well, it does go down, seems to be going down from this point, -2, -3, -4, the order here. But we are giving it 10 times more points in each step. And it only declines by, 1 order of magnitude at the best. Maybe even less over here. So the convergence is pretty slow. Here's another approach. Here we can have, so here we're just collecting data from the given number of realizations of the Monte Carlo calculator, but we run this for 1,000 times and then draw a histogram and calculate the mean. So that's another way to find some additional accuracy, to do Monte Carlo in batches, in a sense, right? So we're doing 1,000 batches of Monte Carlos, each having 10,000 points, and then we're taking the mean, and the mean has pretty good accuracy. It's not a game changer, but that's another way to get the accuracy from a Monte Carlo calculation. And here's the distribution. You can see it's centered around. It's around pi. So what are the thoughts, sort of conclusions on the Monte Carlo exercises? Convergence is slow, and that's true. But still, we use Monte Carlos in several scenarios. So simulating random variables from complex distributions is one common use of the method. And here I'm thinking about the economic models first of all. And in a couple of videos, we will see exactly how it's going to work. Of course, Monte Carlo is used a lot in econometrics to test various procedures and estimators. And this essentially entails to generating, different possible data from the same data generating process and then testing the estimators and their performance. Now, computing high-dimensional integrals. Integrals will be the topic of the next video, and we will see that there is a curse of dimensionality in the calculation of multidimensional integrals. Monte Carlo is often the only way to go about high-dimensional integrals that we have sometimes in economic models. Another interesting area of application is that sometimes expressing a problem at hand in the random terms may help breaking the curse of dimensionality of the deterministic problem. So it is possible sometimes to reduce computational load by working with the random version of the same problem. And here's a quite unconventional use of Monte Carlo for analytical proofs, or assisting the analytical proofs. We can do things like this. So if you assume some non-informative initial distribution for the parameters that enter some particular theoretical proposition, and then generate a large number of these parameter vectors, then it's possible to check whether the theoretical proposition is true or not for each of those parameter values, and analyze the patterns of parameters where the proposition does or does not hold. Maybe finding some counterfactual or finding some counterexample is sufficient to move the theoretical work forward. So let's look at this. Imagine that you have a function f of x, and this is just a power function, and this more complicated g of x, which involves a cosine and a multiplier, which is depending on k. Now, is it true that g of x is greater than f of x on the interval 0, 1 for all k's which are greater or equal 1.5? I haven't attempted proving this theoretically, but I think that it might not be a very easy task. Maybe it's easier just to check, right? And so how do we check that? Maybe we can solve a more general model or more general question is, for which values of k does this inequality hold? Well, it's easy enough to organize the following Monte Carlo procedure. Let's have a quite dense grid on X. And then some many draws of the random variables, which we will draw from the uniform distribution with lower boundary of 1.5 and say high 10. Then we have f and x values, and we could just plot these functions. Or we could also write a check, which is the a vectorized comparison. Comparison is here, and we want to see whether all of these comparisons are true along the first axis, the vertical axis. And yeah, I have to make sure that the shapes of these objects are correct. We have different axes on in the columns, I suppose. Yes, different axes in the columns and different draws in the rows. All right. So the case where this does not hold are then stored in this fk, and then we can say whether it fails or it doesn't fail, and if it's failing, then we can also report for which values of k the proposition is failing. And this is the plot, another plot of k's, where we plot k which checked with the green color and k's that didn't check with the red color. So let's see how it works. Oh, I have to go out of the presentation mode. So here's the plot. The simulated proposition is true. Okay, and these are all of the k's that we've tried between the 1.5 and 10. So what happens if I reduce the upper bound? Say, it seems that for the upper bound everything is pretty good. Oh, and suddenly we have this proposition is false. Moreover, these are the values of k, and you can see they're pretty close to 1.5, where the inequality fails. So the theoretical proposition fails. Now, if I increase the number of draws in this Monte Carlo, you can actually have a longer list of cases where it fails, and then probably you can reestablish your bound for k where the proposition holds. So 1.56, it still fails. Okay, so I mean, this would never be able to give you a decisive answer for a theoretical proposition, but it allows you to get some idea of how the theory works. Okay, and so this is what's already said. There is a list of some learning resources, which is primarily documents this time. And that's it for this video. See you next time.